This is a recording of a live webinar filmed on August 23, 2023, the second in our four-part series entitled Expert Insights, Industrial Efficiency. Join us for the two remaining live events, August 30th and September 6th, covering pretreatment and water treatment, or check out past recordings and other demos on our channel. Click the link in the description to learn more about upcoming webinars or to follow us on LinkedIn to be in the loop of upcoming events.
All right, we're going to get started here this afternoon. Good afternoon, everyone. Thank you for everyone who is jumping on the call to attend. Again, the reason for doing this series of webinars is we have FabTech coming up where we'll be exhibiting. You can see on this message here, D40130. We also got a couple sessions that we'll be talking at, including Dave Schimpf doing See It, Touch It, Fix It on Tuesday, September 12th. But one of the reasons we're trying to do these is because, this year, with kind of economic uncertainty, rising prices, and everything that everyone's been dealing with in the past few years, two key things have kind of been standing out. It's been about the cost savings and sustainability, and sometimes those can somewhat go hand in hand. So in today's talk, we're going to be talking about low temperature and phosphate-free cleaning chemistry. Some have been around a while, some of them are a little bit newer. And doing this talk today is Dave Schimpf. Dave Schimpf, he's been with DuBois Chemicals for 31 years, and he's done all sorts of things across the board. He's been a bench chemist. He's been in marketing, tech support. He's been out in the field. He's been product management, business development, and currently he is our VP of R&D across the entire company. Holds a lot of patents in pretreatment, and he is also a member of CCAI, PCI, and not pertaining to this, but equally important in my book is the Brewers Association. So with that, I'm going to let Dave take over talk here. If you have any questions, please feel free to type them in the Q&A. We'll either answer them as we go or we'll wait till the end. And then we can go from there. So without further ado, Dave.
Thanks, Max. I appreciate it. All right, so the focus of today's talk is going to be on cleaners, and we're going to spend some time, particularly early on, talking about how we develop cleaners, how we look at cleaning from a big picture. We're going to talk about some ingredients and some flexibility we have, and that's going to play into what we do with low temperature cleaning technology and some of the direction that we see cleaners going over the next, say, 10, 15 years. So that's the way we're going to do this. So Max already talked about that. Let's just say I've been at this for quite a while. All right, so let's start with, what is a soil? Soils can be lots of things, right? It could be fingerprints, it could be metalworking fluid, it could be oxidation on the surface of a metal. It could be just things that stick to a surface from being in your plant for a period of time. But our job is to remove those soils. And the first thing we need to do is start to break or disrupt the bonding forces that occur between the soil and the substrate. Some of those are very weak forces. Some of them are very strong. And we have to come up with a formula or a strategy to break that or disrupt that soil so that we can get it off the surface of whatever it is that we're trying to clean. So there's several mechanisms we can use to do that. So one, maybe the most common one we think about is saponification. And this is where we're using an alkaline material, something like caustic or carbonate, to react with a fat that's on the surface. And that reaction causes that fat to be turned into a soap, hence the term saponification, and it makes it more soluble in water. This is going to be important in metalworking fluids, in applications outside the metal finishing area, but it's also important when it comes to things like fingerprints, because the primary soil that ends up on a part from you handling it is the oil on your hands. Emulsification is a second method, and that's where we're taking the soil that's on the surface and making it more soluble or dispersible in the cleaning system that we have. Wetting is another mechanism. And when we talk about wetting, what we're talking about is reducing the surface tension of the metal substrate, or maybe it's a plastic substrate, but changing that surface tension so that the soil no longer wants to stick to that surface. It could also be a penetration, if you will, of the soil so that it will more easily release. The last mechanism that I'm going to talk about is another type of reaction. Maybe it's an acid-base reaction, and this could work both for soils that are acidic in nature on the alkaline side, or it could be things that are alkaline in nature. Let's say a scale or rust that's on the surface, and now I'm going to build a cleaner that's acidic in order to react with that substrate and help to make it more soluble in water. Other things that we want to do in our cleaning formula to make sure that it's efficient and meets the needs of our end application. So one of the things we'll do is build inhibitors into our formulas. Inhibitors do a couple of things. One, they can protect the substrate from attack during the cleaning process. It might just slow that reaction rate. It might actually, in some cases, it's beneficial to have some attack on the substrate. But I'm going to add inhibitors so that I'm either removing material at the right rate or I'm protecting against attack. And then, of course, you want to leave some of that protection behind before it goes to the next step in a particular process. The second thing I want to do is I want to soften or control hard water salts that might be either in your makeup water or that build up in the system over time. We can do that through the use of chelators and sequestrants, and we'll talk about those at more length later. We also will add ingredients to our cleaners that improve rinsability. And there's a couple of different ways of doing that. One we already talked about in that mechanism where we improve wetting or sheeting on a surface. We're also going to add things to that system that will protect against redeposition of soils. This is particularly important when we're talking about immersion cleaning processes. Go ahead, Max. All right, so if I'm building a product, I'm just kind of running through some of the ingredients, and then we'll talk about why they're important. So yes, water is an important cleaner, but now I need to add other things to it. So first, I'm going to have builders. If I'm working on the alkaline side, I'm going to add things like caustic or carbonate. If I'm adding on the acid side, I might use a mineral acid. I might use something like citric or glycolic acid. But I've got to have something that shifts that pH and makes the soil that's there more reactive or more soluble in water. I'm going to add surfactants, and we're going to spend a lot of time talking about surfactants in a minute. But surface active agents, it's a compound word. We're going to add those. They give us detergency. They give us dispersancy. They give us wetting and sheeting properties. There will be other additives. We talked about inhibitors already. We might also add defoamers to a cleaning solution depending on the application. We'll talk about where that's going to be important later. And then solvents. And you can add things other than water to your matrix that will speed the rate at which either something solubilizes or effectively you're using the solvent to change the way the thing melts. And we'll talk about why here in a little while. So, of course, water is important. And I don't know if I can spend enough. Actually, we've written articles on this before, the importance of water. So, one, water is the universal solvent, or at least that's the way people talk about it. Almost anything will solubilize in water if you're given it enough time. If you heat the water up, you'll speed the dissolution of things into water. But water quality is really important. So the total dissolved solids that are in your water, in your cleaning solution, actually change the rate at which it cleans. The cleaner the water, the faster you can clean. And hardness is important. And what I mean by that is calcium and magnesium ions that build up in the tank. If I have a way to either minimize their inclusion in the tank, or I can control the impact on the overall cleaning solution, I get better results, better cleaning, and longer, cleaner life out of the product. We did a study several years ago where we were able to prove to ourselves that we saw a 20 to 25% reduction in cleaner consumption just by keeping the hardness salts out of that first stage or out of the cleaning stage. So really important if you can use good, high quality water. Go ahead, Max. All right, so let's break down ingredients a little bit. So many ferrous metal cleaners are built on these first two items, potassium and sodium hydroxide. Give us great performance with heavy, fatty soils. Why? They're using that saponification reaction in order to help remove the soils. So you will see these frequently used. Another pro, although we don't have it written down here, is cost. Sodium hydroxide, potassium hydroxide, that base in that cleaner is relatively cheap. On the negative side, high pH, which means you've got an HS&E concern. It can be corrosive to substrates. It certainly can be corrosive to skin, so you got to watch that. If you don't take care to formulate with other ingredients that improve rinsability, caustic by itself is very difficult to rinse. It doesn't want to come back off the surface. And obviously it's going to attack soft metals. So you've got to formulate carefully or be very careful in your product selection when you've got yellow metals or white metals that you're trying to clean. Next one, silicate. Silicates kind of get a bad rap. So I'm going to talk about pros and cons for that. One, it acts as an inhibitor on things like aluminum. So it'll actually slow the attack on aluminum when used in combination with other ingredients. We will often formulate caustic, so either sodium or potassium hydroxide with silicates in order to slow the rate of reaction on a soft metal. Silicate also acts as a dispersant. It will grab a hold of soils and help to improve solubility. There's an old cleaning term called peptizing, where it actually bonds to things that don't want to be soluble and actually helps to make them soluble. So silicate is an effective peptizer. And it can be added not as necessarily as a wetting agent, but as a sheeting agent. Silicate actually improves the rate at which you can rinse. So added to caustic, it makes it a better rinsing material. Now, here's the big negative. Silicates can result in scales that are very difficult to remove if you use high temperatures. So in high temperature cleaning applications, we generally do not use silicate. All right, next one, phosphates. If they didn't have environmental problems, phosphates are wonderful cleaners. They're less corrosive than caustic. They buffer pH effectively. They peptize just like silicates do. Actually, they're better at peptizing and work very well as a detergent by themselves. On the negative side, they're certainly less effective than caustic when it comes to reacting with things like fats. And then, of course, there's wastewater concerns. So if we introduce too much phosphate into the environment, we deal with this thing called eutrophication. So we almost globally now have cut way back on our use of phosphate other than for fertilizer. And because of this, you won't see it very commonly in cleaning applications anymore. Last one I'm going to talk about here on the aqueous side is carbonates. We can use carbonates or bicarbonate, certainly less corrosive than caustic, generally lower cost than some of the other ingredients on this list. In some cases, or formulated properly, can give you some corrosion inhibition properties. Certainly not as effective because you have to use quite a bit more of this material in comparison to caustic or phosphate in a formulation. Okay, go ahead, Max. So from an inhibition standpoint, these are the things that we will add to a cleaner for inhibition. Silicate is one of the things we'll add for soft metals. So it protects the cleaner from attacking the substrate. We will add that when it's appropriate, when the temperature of cleaning is appropriate for using silicates. Very common in general purpose cleaners, where you add a small amount of silicate to give you some protection, but also to improve rinsability. Now, we can also add inhibitors that improve corrosion properties after cleaning. So these are things like nitrites. We can add nitrite to a solution, and that at the right at the right part per million levels, nitrite provides long-term corrosion inhibition. We can add amines. The amines that you add both buffer, improve your pH. It raises the pH in the solution, but it also has a tendency with other ingredients to provide corrosion inhibition. And the same thing for borates. We can add borates to cleaners that will provide corrosion inhibition after the product is cleaned. Go ahead, Max. Water conditioners. So I mentioned this earlier about water quality. So water quality is really important when I'm cleaning a substrate, but sometimes I don't have the ability to control how much hardness is going to get into a solution. So this is where we're going to build a cleaner with things like sequestrants, phosphates, or gluconates. These are things that loosely hold on to the hardness ions, but don't tie them up permanently. Or I can add chelants, things like EDTA or NTA. Even phosphate can be used to more tightly hold on to calcium and magnesium in solution and keep it from interfering with the cleaning process. There are also different polymers or additives that can be used to do the same thing. These all soften the water. You've heard that term before, and the idea of softening the water is to allow the rest of the ingredients in your formula actually work on the soil rather than interacting with those hardness ions. Next really important property of a cleaner is to have some type of dispersancy. So I take a soil that's not typically soluble in water, and now I've forced it to be soluble in water. I don't want it to redeposit. I don't want it to go back on that surface. So the list of ingredients that are here, things like polymethacrylate, surfactants, sequestrants, silicates, some other polymers, all of these things can be added into a cleaning solution to help keep the soil from redepositing on the substrate and becoming a problem later. Solvents. Solvents sometimes get a bad rap. We've got things like VOCs that people talk about. We've got concerns about health with certain solvents. What I'm talking about here are solvents that are added to aqueous cleaning solutions that what they do is they improve the rate at which you penetrate a soil. So if I've got a soil that's been on a substrate for months and it's been allowed to dry, and now that soil starts to oxidize, and as it oxidizes, the bond between the soil and the substrate becomes more and more tenacious. The solvent actually helps to break that bond between the soil and the substrate, just like a wetting agent does, just like a surfactant, but it can do it more rapidly. Now, we talked about the negatives, things like air pollution, fire hazards. They can be an irritant. In many cases, adding solvents is a higher per gallon used cost, but you may be in a situation with your application where your soils are very difficult to remove. Now, a positive could be, I'll take a soil that normally I have to clean at 160 degrees because it doesn't want to solubilize in water. That solvent added to that solution may allow you to drop that temperature by 20, 30, 40 degrees, and that offsets that negative enough that you want to use a solvent. Go ahead, Max. So the next couple slides, I'm going to talk about surfactants, because this is really an important focus area of this talk. We're going to talk about how do we develop low temperature cleaners. And I think that's, I'd say over the last 10 years, we've seen a lot more focus on let's reduce energy. How much energy are we going to use in a cleaning process? And surfactants are really the key ingredient to helping us get to that. So I want to explain some of the properties of surfactants, how they work, really how they're made, or how they're made up. So that's what we're going to do in the next few slides. So surfactants are multifunctional. They wet soils. They can emulsify soils, so an oil, once you remove it, they're good at suspending and dispersing soils. They keep things from redepositing on the part. There are surfactants that are appropriate for spray, for immersion, and some that bridge both applications. And things we're going to talk about are surface tension, cloud points. We'll talk about those over the next couple slides. I think I got ahead of myself here. So they work as surface active agents. They change the properties of that substrate. They make water wetter effectively. So it allows the water to penetrate. Rather than forming a droplet, it spreads on the surface. So it allows other ingredients. So caustic is not a wetting agent. And caustic will only react with a fat on the surface of a part as fast as it can get there. If you use a wetting agent, it spreads it out and improves the rate at which that caustic will penetrate that soil and that allow that saponification reaction to occur. So it ends up reducing the surface tension on the substrate. In some cases, there isn't a reaction, but that reduction of surface tension allows that soil to literally roll off of the part. And then we're going to talk about cloud point and how that property is important. So surfactants is emulsifiers. What a surfactant does is it surrounds droplets of oils or soils, and I'm going to show on the next slide how it does that. But this is just a graphic of the yellow dots, if you will, around this black dot, or the way that the surfactant surrounds an oil droplet. And because it does that, it surrounds that oil droplet, it becomes more soluble in water and allows you to suspend that soil in the cleaning solution. So surfactants are made up of molecules. They're engineered where you have one end that is hydrophilic, meaning that it loves water and it's going to be soluble in water. It also has a hydrophobe, or a water-hating end. Some people use the term lipophile. That means it's fat-loving. So we usually refer to that as the tail, and that tail will solubilize in your oil phase, while your hydrophile, or your water-loving end, will be soluble in water. Now, surfactants like to line themselves up. They orient themselves along interfaces or surfaces. So this picture is very correct in the way a surfactant behaves. The surfactant will line itself up along the surface even, and this is how it reduces surface tension. The water or hydrophilic end will end up being right at the surface of the water, and the tail's literally sitting on top of the surface. That's how it changes the properties of water, changes its surface tension. Surfactants also form micelles. So by themselves, in the solution, of course, the hydrophilic tail is not soluble in water. So how does it exist, or how does it not separate from the solution, try to float to the top? Well, we saw that it does separate to a point, but they also will form micelles, which is basically little oil droplets for lack of a better description, where the tails all associate with themselves, and then it surrounds itself with this hydrophilic outside. Now, when it's introduced to an oil or a soil, then it does the same thing, but now the tails end up becoming part of the oil phase, and the heads or the hydrophilic end ends up part of the water phase. All right, now, this is really important when we're talking about low temperature cleaners. Every surfactant is characterized by something we call a cloud point. The cloud point is the point at which the surfactant no longer wants to form a micelle in solution. So there's two properties there. One, concentration is important. How much surfactant is there is important. I've got to have enough in solution to form those micelles. But I've also got to be at a temperature at which the surfactant is still in solution. So below the cloud point, you will see very clear solutions, and that's where the surfactant is, I guess, the solubility on the water side is the highest. When I raise the temperature and I get to a point where it starts to separate, now I'm at a point where it clouds. We're going to show you a picture here in a minute. But what you'll find is that's the point at which that surfactant is the most effective. So when we build a cleaner, we're trying to build a cleaner right in the temperature range that we expect that detergent to work best, right around the cloud point. If the temperature gets too high, the surfactant actually separates from solution completely, and it behaves like a soil. If I operate well below the cloud point, your solubility is high on your surfactant. Unfortunately, it's also foamy at that point. So that can get in the way of reactions, and it's not as effective at lower temperatures than it is right around its cloud point. So we take advantage of that behavior as we're developing cleaning solutions based on where we want to operate the temperature and what soils we're working with. Go ahead, Max. Yeah, so here's a picture of a typical study that we will do in the laboratory. The top picture, this is a surfactant in solution and at a temperature at which the surfactant is very much soluble. The picture below is where we've heated that same solution up, and now you're starting to see the solution become cloudy or hazy. And that's where the surfactant is just starting to separate from the solution. If I heated it up quite a bit more, it'll actually separate, float to the top, and create a second phase. So I want to operate right in that area where it starts to cloud. That's probably the most effective temperature at which to use the surfactant as a cleaner. All right. So as we think about immersion and spray, do we develop cleaners the same way for both applications? And the answer is absolutely not. So if I'm going to spray a product, one of the big challenges is foam. So I want to make sure that my spray cleaners are low foam. When I'm using surfactants, I'm going to make sure that they're operating right around the cloud point, maybe slightly above the cloud point, so that I don't encourage foam to occur. And I'm also going to develop that product based on the soil matrix, because I may have for example, let's say I've got a waxy soil on that surface. That wax has got a melt temperature that I'm trying to get to. So I might take advantage of temperature, solvent, and surfactant to speed the rate at which that soil solubilizes. But I don't want to overdo it. And if I run too low, let's say I pick a product that's got a cloud point of 160 and I'm running at 140 degrees, I'm actually going to start to introduce foam. So I don't want to do that. Now, on the immersion side, I can tolerate more foam. So I will use products that are a little foamier, I may use certain types of surfactants which have broad cloud points. That is, they're active across a broader temperature range. And that allows me to take advantage of those types of surfactants that can be very good at penetrating oil or soil, but have some fun. Now, another important point between immersion and spray applications. Generally speaking, we aren't as concerned about emulsifying soils in a spray. And that's because the part never actually sees the working solution. It sees the solutions that's sprayed on it. So as the oil's removed from the part, I want it to separate from the cleaning solution so I can skim it off and keep my tank clean. In an immersion operation, that's not true. I want to build the product most of the time so that it penetrates the oil and it emulsifies the oil, because as I drag parts back through the cleaning solution, I want to redeposit that layer of oil that might be forming at the top on my parts. I want to make sure that it ties it up so that I pull it out my part sheet effectively. All right, Max, this is just an intro slide. I'm going to talk about some individual products. But one of the things I want to talk about before we jump off there is just how do we measure quality from a cleaning perspective, both in the field and the laboratory. So one of the things I'm going to look for, and unfortunately I don't have I've got a few pictures here, but I don't have great pictures here on some of these. One of the things we look for is water break. So on the surface of a part, if I've got a soil there and I spray water on it, water's going to do one of two things. It's either going to bead on that surface or it's going to sheet from the surface. If I see beading on the surface, that generally means that I've got a soil left behind. So I don't want to see beading like I see on the surface of my car. The surface of your automobile has soil. It's called wax. And that wax is there to cause it to bead and to get the water droplets to sheet off. It's part of the sheen of your car. But on a metal part or a plastic part that I've got some other process for, I don't want to see that. I want to see that thing sheet. I don't want to see areas where the water breaks on the surface, because those break points tell me there's soil left behind. I might also use, I know this sounds simple, but a white towel. I might wipe the substrate, and I'm looking to see if I get any soil that comes off on that white tile after I'm done cleaning. It might be oxides that come off. It might be oil that's still there that I can physically see on the towel. I also use tape pull. It's not as frequent. We don't use that quite as much for cleanliness. Certainly in our laboratory, and I'm going to show you several pictures of this in our cleaning examples, is Blacklight. Many of the soils that we clean from surfaces of parts are sensitive to blacklight, or they're phosphorescent. And I want to look for the absence of that phosphorescence. So you'll see that in some of these photos coming up. Certainly, you can use an analytical lab. We've got lots of test methods that we use to further analyze soil, whether it's things like FTIR, OSEE. There are several other methods, but generally speaking, those are laboratory analytical methods. Those aren't something that you're going to do in a production environment. All right, so the next, I think 7 to 10 slides, something like that, I'm going to talk about some particular cleaners. They're cleaners that we've developed over the years. I'm going to talk about how they're formulated and then effectively why, and then I'm going to give you an example or two of where we've used them and been successful with them in the past. So GF Clean 465. This product is strongly alkaline, built with caustic. It is water conditioned, so we have materials in there to protect against hardness developing in the solution. Certainly, we have surfactant dispersants that are built into the product. This product is very concentrated, and developed that way so that it can be used at a relatively low concentration. Our target concentration for GF Clean 465 is 2 to 3%. Most typically used on things like iron and magnesium. You generally don't use GF Clean on, or GF Clean 465 on aluminum. Go ahead, Max. So here's an example of an application where we've used GF Clean 465. I know we use this on these parts, we used the product at 3%. The exposure time for these parts was about 90 seconds, and we ran at about 125 degrees. Now, the reason we ran at 125 degrees, we had a forming fluid. You can see that first part, that's a raw part. The raw part had a forming fluid on it. I believe these were tubes that were being formed, but these tubes, this forming fluid is very sticky, and as it ages, it oxidizes. So in order to remove that soil effectively, we need a little bit of heat. We needed good penetration from the surfactants in the 465, and then we needed the caustic that was there to help saponify and pull it from the surface. So system 2 is the best result. We tested a couple other products, but system 2 was the 465, 3%, 90 seconds, and 125 degrees. All right, so GF Clean 752M. Similar name, slightly different formulation though. This one's got moderate alkalinity, so it doesn't have near the caustic that the 465 does. It's silicated. So this product, we made sure that it was built for mixed metal applications. So this can be used on caustic, or on ferrous metals, but it can also be used on things like aluminum or galvanized and not worry about attack on the substrate. There are water conditioners built in again. This one's low temperature or low foaming, even at low temps. So this one's got surfactants in it that have a cloud point that allows us to run at lower temp. Again, it's concentrated. Most of our products, we build them so that we can use them in that 3% range. So here's this particular product. This was an interesting case study. We were running both aluminum and steel parts, and these parts were having to be prepped for over-the-road tractors. I'm talking about tractor trailers. So the aluminum parts had both forming oil and release agents on it. The steel had some forming and stamping fluids on it. So we needed a product that we could process both parts in a spray and allow us to, one, clean effectively, because you're going into a pre-treatment process afterward, but you got to be safe on both substrates at the same time. So we were able to use the 752 at about 120 degrees. The cleaning time was under 60 seconds. What was interesting about this was we were able to replace a solventized product that had used a solvent in it in the past, and still able to meet the very stringent paint requirements that were for this tractor trailer manufacturer. So, of course, the pre-treatment is really important at hitting the target from a paint performance perspective. But if you don't clean the parts first, you're never going to get that pre-treatment to work. So, really important case here where cleaning up front was key to making sure that you could pass that stringent tractor trailer spec. The next product is, I'll just tell you that if my lab manager was on here for our surface finishing group, she would tell you this is our go-to product. GF Clean 1052, we'll recommend this product for many ferrous and less non-ferrous, but many ferrous applications. Moderately alkaline, does a great job at conditioning hard water. It's always low foaming in the temperature ranges that we'll use it. 115 degrees is kind of a sweet spot for this product. No silicates, no phosphates. We'll use it for ferrous, for copper when needed. We'll use it on magnesium. This next application, we ran it at 3%, again, formulated for 3%. This is actually under Blacklight. You can see how nasty that ferrous part is up on top. It's got soil blotches all over it. Again, this looks like it was a forming fluid. Cleaned it at 3% in 40 seconds at 115 degrees, and you can see the result from below. There's really no soil left at all on that system. Not the only place we've ever used 1052. If Max were speaking, he'd tell you I think it's our #1 cleaner at this point in our product line. All right, next one. All right, this is a neat formula. GF Clean 5787U. I like to call this a kitchen sink product. It's got a little bit of everything. Moderately alkaline, but it's still beefy. It's still got plenty of alkalinity to it. It can be used in mixed metal applications. So we made sure we have inhibitors in there to keep the alkalinity from going after softer metals. It's low foaming. It is very soil tolerant. So we built this product so that as the soil builds up in the solution, it doesn't worry about it. It just keeps cleaning. And then it's also got corrosion inhibition properties in it. So if you needed to use it, it is an in-process cleaner where your next step was going to be some other operation and the parts were going to sit. This product is very effective. It was originally developed for remanufacturing operations. So I won't mention customer names, but people that would bring parts in, disassemble, clean them, and then reassemble parts. This product's very effective in those applications and built to handle the heavy soil loads that result from those. Now, this next couple of slides, these are actually bakery pans. And if there's anybody online who works in a facility that makes these, they understand how nasty the soils are. It's very difficult to form these shapes in these parts and still get them clean. So the raw parts you can see on the left-hand side, you can actually see some of the soil in those parts up on the top, the waviness that's there in parts. That is a forming oil that's left behind. In some cases, it's almost got the consistency of honey, so it's very sticky, very difficult to remove. But I'll show you the next slide. At 3%, believe it or not, 20-second application time at 140 degrees, we're able to take them from the parts on the left under Blacklight to the parts on the far right. Complete soil removal in 20 seconds. This is really a remarkable product, how well it works. This particular application, because of the type of soil, the temperatures necessary, it's still appropriate for lower temperature applications when needed. All right, metal Turge. Metal Turge was developed specifically as an in-process cleaner. So this is for someone, let's say they're machining a part, they want to clean, remove the chips from the part, and provide some corrosion inhibition prior to going to the next step in a process. So that's exactly what metal Turge was built for. As it turns out, it's also multi-metal safe, so it could be used on ferrous and non-ferrous parts without any trouble. Built to be run at low temperature, so it's something that can run in that 100 to 110 degree range. Low pressure or low foam, even at high pressure. So the surfactants that are in there are ones that can be run at high pressure. We've used this in something like a Prosecco washer where your pressures are up 200 psi and it still does a good job controlling foam. Does provide short-term rust inhibition, and it's got a very moderate alkalinity. We say medium here, but I'll call it moderate alkalinity. Go ahead, Max. So good case study on this next one. So This customer was a refurbisher of gas bottles. So you can see the picture here. Obviously, I'm not going to mention who that person or that company was, but they're bringing these things in. And of course, they're loaded up with soil, right? A lot of these bottles come back from somebody who's been using them under their gas grill for the last 2 years. And now it's got caked on food soil, basically fats that are all over the outside of these parts. They struggled with these parts in two ways. One, they had problems with the grease that would build up. But the second thing they struggled with was bleed through, because a lot of these tanks will also end up corroding over time as they sit under your grill. So we were able to do two things with Metal Turge. We were able to reduce the temperature at which they'd been running the process, because they'd been running the process hot before. So they're able to reduce the temperature, and then the concentration we were running at, I think we got it down to 1.5%, and they were still able to effectively clean these things. Now, they're already painted, so really all they were trying to do was clean them up enough that they could reapply a paint to that surface. But they were running so many that it needed to make sure there wasn't any flash rusting between processes. So the Metal Turge did a very effective job of preventing that bleed through or that flash rust after the cleaning process. All right, next two products, or last two products, I'm going to talk about are immersion products. So Make Your Clean 3620 NA. Made for immersion, highly alkaline. It is silicated, and it's silicated for rinsing and detergency. So you get that peptizing effect from silicate, but it also improves the rinsability of the alkaline cleaner. It was built for long tank life. So this product isn't, it's not 5% active ingredients. This thing is loaded with goodies so that this stuff will live in the process tank for long periods of time. This particular immersion product is lower foaming. It doesn't have much of a foam hit. The next slide is where we were using this at a gear manufacturer. So they're hobbing gears. The hobbing process creates a very tenacious soil. You can see the raw part underneath under Blacklight. You can see that this thing's just covered with what looks like almost a dust. So that's what we're trying to remove. We immerse the product, and of course, immersion doesn't give you the same impingement that spray does, so you need a little more time. But it was only 7 minutes in the operation, about 140 degrees, and you can see that all the soil was removed, particularly under Blacklight. It's very obvious that you removed all the soils that were created in that hobbing process. All right, and then the last one I want to talk about is Uniclean 58DA. This again was built for immersion, very heavy-duty alkaline product. It's got good dispersancy, so it keeps the soil from redepositing on the surface. And in this particular case, the immersion product is heavily emulsifying. So as the oils are removed from the part, we want to make sure they're emulsified. So as you drag the parts back up through the cleaning solution, you're not redepositing that oil on the surface. I think the next slide really shows that. These parts were being formed. You can see, particularly on the inside of that collar, the soil that's hanging up on that surface. So these were done in a large basket. They're tumbled. You get a little bit of part-on-part action, but not a lot. And then as you know, our Uniclean 58D, it penetrates those soils, it pulls them off, but as you bring the parts back up out of the solution, you do not see redepositing on that surface. Does a very effective job emulsifying and keeping those soils from redepositing on the surface. All right, so I think that is my list of highlights. Max, I'm not sure if you want to introduce this next slide, and then we'll come back to questions.
Yep, no, that's what we'll do. Dave, again, thanks again for doing all this. That was great stuff there. Again, you have his information here if you'd like to reach out, if you have any questions about what you saw or just need to talk. Again, we're going to be at FabTech. Just as a reminder, that's our booth number. We got a couple people speaking, which is going to be nice. And then next week, we're going to have Michelle Bloomfield talking about zirconium and how you can improve your paint pretreatment process there. Just a couple questions popped up for it. One person asked, can I use a dyeing test for my cleaning process? Is it better or worse than the other methods you mentioned?
Yeah, I failed to mention it. Dynes testing is particularly important when you're using a coating on a surface. Let's say, actually, the bakery pan example that I had earlier was a really good example of that. In some processes, we're cleaning the metal in those bakery pans. We don't actually put a pretreatment down. You're trying to get that surface clean, and then you want to leave it in a certain dynes range so that when you apply the glaze, it actually wets out and then cures effectively. So it really depends on your process. Sometimes that dynes range and understand dynes is a measure of surface tension on the surface. So sometimes it's really important to future processes what that dynes rating is. So I'm not going to tell you it's not important, because I can change the dynes test based on two things: soil remaining on the surface and the wetting agent I use. So if I use a super wet or something that really wets the surface, it can shift that dynes rating without you really wanting me to do that. So when you're doing that, it's really important to discuss that with whoever your supplier is, and then we'll work with you to decide, okay, what is that best dynes rating going to be?
Another question we got here, Dave, is are there any recommended standards or specs for defining cleanliness on a steel or aluminum surface? When setting up a new cleaning process, we struggle to find cleanliness. For instance, how clean is clean?
Yeah, that's a great question too, in this sense, because how clean is clean depends on whatever your next process is. We talked about Metal Turge, was a product that was developed primarily for in-process cleaning. And most of the time, when you see the parts come out of a metal, and this isn't in slam on Metal Turge, it's the process, that Metal Turge product wouldn't be clean enough, let's say, for a pretreatment operation where I want to put zirconium on it next. But it really has to be defined by what is your next process. If your next process is pretreatment, it's got to be very clean. And we can use dynes testing, we can use blacklight testing to prove. There are methods I mentioned. You can do it through OSEE. You can do particle counts and look to see how much particle residue is left behind the surface. But it really comes back to what your next process is. If we defined it the same way for everybody, you'd be overdoing it for so many processes. So it's really important to get into the detail of what is my next thing I'm going to do. And then you define what cleanliness should be.
And then I guess the last one would be just, are there any additional regulations? We heard you talk about phosphates. Are there any additional regulations from the EPA or anyone else on any raw materials that we see coming up, or kind of what's that landscape look like?
Actually, Max, since we've got about 5 minutes and someone else can pop up and ask a question, that's great. But I got several things I wanted to talk about there. One, I think over the next 10 years, we're going to see a lot more development from the sustainability side. And what I really mean by that is not just raw material restrictions. We've been dealing with phosphate restrictions for 25 years. We still use phosphates in certain applications, and I think we'll continue to use phosphates, but we're going to continue to reduce their use. Where I do see growth or change over the next few years are surfactants that are either derived from natural sources, so plant-based Surfactants, I think, are going to become more and more important. Certainly, they have to be biodegradable, and just because they come from a plant source doesn't mean that they're going to be easily biodegradable. So we're going to have to continue to look at that. Some of those surfactant sources or feedstocks, if you will, are more expensive. So I think both regulatory environment and social environment are going to continue to push us more and more toward surfactants that are derived from natural sources. I think we're going to continue to see restrictions on chelants. Chelants can be a problem for us when it comes to wastewater and how we treat wastewater. But I think you're going to continue to see some restrictions in how some of those products are used. And if you have reversible sequestrants, and there are materials out there that actually, when you change pH, quickly release the metals that they're tying up, I think you're going to see more and more in development in that area. We've seen some of it over the last 10 years, but I think we're going to continue to see more. Boron. We're seeing restrictions in the use of boron in Europe, and Europe is usually they usually lead the way. So I expect that we're going to see fewer and fewer products being built from boron or borax materials. They've got nice advantages, but the toxicity profile isn't great. So I expect over the next few years we'll see further restrictions on the use of boron, or at least restricted to critical applications as opposed to broad applications. Trying to think. I think those are the four key areas: sustainable surfactants, from biologically derived or naturally derived substrates, chelants, reversible sequestrants, and then I think we'll see some further restrictions in boron use over time.
Excellent. With that, I do not see any additional questions. So since we're getting near the end, I think this is a decent time to wrap it up. Again, Dave, thank you so much. That's a great presentation, a lot of great information there.
Yep. And you can see my email out there. So if you've got a specific question you were afraid to ask in a public forum, send me an email. I'll get back to you.
And just a reminder again, next Wednesday, same bad time, same bad place. We are going to be having Michelle Bloomfield talk about zirconium from 1 to 2 p.m. Eastern Standard Time. But if you don't get a chance before that, please feel free to visit us if you're going to be in Chicago for FabTech. We're going to be there all 4 days. Got a couple talks there. So again, thank you everyone who jumped on. We're going to make this available on YouTube in the next few days. And take care.